11. Capstone, forecasting the number of anti-diabetic drug prescriptions in Australia. This section presents a comprehensive capstone project, challenging you to apply the full spectrum of time series forecasting techniques learned throughout this book to a real-world problem, predicting the number of anti-diabetic drug prescriptions in Australia. This exercise will consolidate your understanding of data exploration, stationarity transformations, model selection, parameter tuning, rigorous model validation, and robust forecasting methodologies like rolling forecasts. The goal is to develop a robust forecasting model that can accurately predict future prescription numbers, which has significant implications for healthcare resource planning, supply chain optimization for pharmaceutical companies, and public health policy. 11.1 Project Setup and Data Loading. The first step in any time series project is to load and understand your data. We will be working with a dataset representing monthly anti-diabetic drug prescriptions in Australia. 1.1. Importing necessary libraries. We begin by importing the essential Python libraries for data manipulation, time series analysis, and visualization. Download the code on OnePageCode Substack. This initial block imports a standard set of libraries. Code snippet is crucial for data handling, code snippet and code snippet for visualization, and code snippet for core time series functionalities like decomposition and plotting ACF/PACF. We also bring in code snippet for automated ARIMA parameter selection and code snippet for evaluating our model's performance. Suppressing warnings and setting a consistent plot style enhances readability. 1.1.2 Loading and initial data inspection. The dataset is typically in a CSV format. We load it using code snippet and ensure the date column is correctly parsed as a datetime object and set as the index. This is a fundamental step for time series analysis, allowing code snippet to recognize the sequential nature of the data. Download the code on OnePageCode Substack. Here, we load the CSV file. The code snippet function is used to convert the month column into a proper datetime format. It's important to specify the code snippet argument, e.g., code snippet, to ensure correct parsing, especially if your dates are not in a standard format. Setting this column as the data frame's index with code snippet is crucial for time series operations, as it allows functions to inherently understand the time ordering. The code snippet and code snippet calls provide a quick overview of the data structure and types. 1.1.3 Visualizing the raw time series. Visualizing the raw time series is the most critical initial step. It allows us to intuitively identify key characteristics such as trend, seasonality, and any irregular fluctuations. Download the code on OnePageCode Substack. This code generates a simple line plot of our time series. From this visualization, we should observe trend is there an overall upward or downward movement over time. For drug prescriptions, an upward trend due to population growth, aging, or increasing prevalence of diabetes is often expected. Seasonality. Do patterns repeat at regular intervals, e.g., monthly, quarterly, yearly? This is common in many real-world datasets, including healthcare, where factors like flu season or holiday periods might influence prescription rates. Cycles. Longer-term fluctuations that are not fixed in period. Irregularities. Random noise or unexpected spikes/dips. Understanding these components from the initial plot guides subsequent pre-processing steps. 11.2 Time series decomposition. Time series decomposition is a statistical task that breaks down a time series into several components: trend, seasonality, and residuals or noise. This helps in understanding the underlying structure of the series and informs decisions about how to model it. 1.2.1 Understanding decomposition. The code snippet function is a powerful tool for this purpose. It supports both additive and multiplicative models. Additive model assumes the components add up, $YT equals TT plus ST plus RT dollar. This is suitable when the magnitude of the seasonal fluctuations does not vary with the level of the time series. Multiplicative model assumes the components multiply, $YT equals TT backslash times ST backslash times RT dollar. This is more appropriate when the magnitude of the seasonal fluctuations increases or decreases with the level of the time series, which is of 10 the case with data showing exponential growth. Given the typical growth in prescription data, a multiplicative model is often more suitable, as the seasonal variations tend to become larger as the overall number of prescriptions increases. Download the code on OnePageCode Substack. In this code, we use code snippet with code snippet and code snippet because our data is monthly and we expect annual seasonality. The code snippet argument is crucial. For monthly data with yearly seasonality, it should be 12. The code snippet method conveniently visualizes the original series, trend, seasonal, and residual components. Interpreting these plots. Trend component shows the underlying long-term direction of the series, smoothed out from seasonal and irregular variations. Seasonal component captures the repeating patterns within each period, e.g., each year. Residual component represents the remaining variation after the trend and seasonal components have been removed. For a good decomposition, residuals should resemble white noise, random fluctuations with no discernible pattern, although some patterns might remain, indicating that the chosen model, additive/multiplicative, or period might not perfectly capture all aspects. 11.3 Achieving stationarity. Many time series models, particularly the SARIMA family, assume that the time series is stationary. A stationary series has constant statistical properties over time: constant mean, constant variance, and an auto-covariance that does not depend on time. Non-stationarity often manifests as trends or seasonality. 1.3.1 Why stationarity matters. Non-stationary series can lead to spurious regressions, where two unrelated series appear to be correlated simply because they both have a trend. Differencing is a common technique to remove trend and seasonality and make a series stationary. 1.3.2 Applying differencing. Based on our decomposition and initial plot, we likely observe both a trend and seasonality. This suggests we'll need both non-seasonal and seasonal differencing. Download the code on OnePageCode Substack. Here, code snippet performs a first-order non-seasonal differencing, effectively removing a linear trend. Then, code snippet performs a seasonal differencing with a period of 12, targeting the annual seasonality. The code snippet method removes the code snippet values that appear at the beginning of the series due to differencing. The plot helps us visually confirm if the series now appears to fluctuate around a constant mean with constant variance. 1.3.3 Augmented Dickey-Fuller, ADF, test, optional but recommended. While visual inspection is helpful, a formal statistical test like the Augmented Dickey-Fuller, ADF, test can confirm stationarity. The null hypothesis of the ADF test is that the time series has a unit root, i.e., it is non-stationary. If the p-value is below a significance level, e.g., 0.05, we reject the null hypothesis and conclude the series is stationary. Load the code on OnePageCode Substack. The code snippet function from code snippet provides the ADF statistic, p-value, and critical values. A low p-value, typically less than or equal to 0.05, indicates that we can reject the null hypothesis of non-stationarity, confirming that our differencing steps were successful in making the series stationary. 11.4 Model selection and parameter optimization, SARIMA. Given the presence of both trend and seasonality, the seasonal autoregressive integrated moving average, SARIMA, model is an excellent choice. A SARIMA model is denoted as SARIMA, P, D, Q, P, DQ, M, where code snippet are the non-seasonal components. Code snippet, order the autoregressive, AR part. Code snippet, degree of non-seasonal differencing, determined in the previous step. Code snippet, order of the moving average, MA part. Code snippet are the seasonal components. Code snippet, order of the seasonal AR part. Code snippet, degree of seasonal differencing, determined in the previous step. Code snippet, order of the seasonal MA part. Code snippet. Number of observations per season, e.g., 12 for monthly data with yearly seasonality. 1.4.1 Finding optimal SARIMA parameters. Traditionally, code snippet are determined by analyzing the autocorrelation function, ACF, and partial autocorrelation function, PACF, plots of the different series. However, this can be iterative and subjective. A more practical approach, especially for a Capstone Project, is to use code snippet, which automates this process by performing a grid search over a range of possible parameters and selecting the best model based on an information criterion, like AIC or BC. Download the code on one Pagecode Substack. Before applying code snippet, we split our data into training and testing sets. The problem statement suggests using the last 36 months for testing, which provides a substantial period to evaluate the model's out-of-sample performance. Code snippet is then called on the code snippet. Key parameters include code snippet, 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 code snippet. Define the search space for the AR and MA orders. Code snippet, code snippet. We explicitly set the differencing orders based on our previous stationarity analysis, though code snippet can also help code snippet determine code snippet. Code snippet specifies the seasonal period. Code snippet enables the seasonal components of the SARIMA model. Code snippet uses a faster, heuristic approach to search for parameters rather than a full grid search. Code snippet provides detailed output of the models tested, which is helpful for understanding the search process. The code snippet will display the best model found, including its parameters and various statistical metrics like AIC, BC, and log likelihood. The model with the lowest AIC, archaic information criterion, or BC, Bayesian information criterion, is generally preferred, as these balance model fit with complexity. 11.5 Model training and residual analysis. Once the optimal SARIMA parameters are identified, the model is trained on the historical data. After training, it is crucial to perform residual analysis to validate the model's assumptions and ensure its reliability. 1.5.1 Fitting the SARIMA model. We use the parameters identified by code snippet to fit the SARIMA model on our training data. Download the code on one Pagecode Substack. The code snippet library's code snippet returns a fitted model directly, so we don't necessarily need to refit using code snippet unless we want more control or to see the code snippet summary directly. The output of code snippet provides all the necessary details, including coefficients, standard errors, p-values, and information criteria. 1.5.2 Residual analysis. Residuals are the differences between the observed values and the values predicted by the model. For a good time series model, the residuals should ideally resemble white noise. That is, they should be uncorrelated, have a constant mean of 0, and constant variance. Any patterns in the residuals indicate that the model has not fully captured the underlying structure of the data, and further improvements might be possible. We check for normality. Are the residuals normally distributed? A QQ plot helps assess this. Zero mean. Is the mean of residuals close to 0? Constant variance. Are the residuals homos? Dostik, constant variance. No autocorrelation. Are the residuals uncorrelated? ACF/PACF plots of residuals help verify this. Any significant spikes suggest uncaptured patterns. Download the code on one Pagecode Substack. The residual plots provide critical diagnostic information. Residuals over time should look like random noise centered around 0, with no clear trends or seasonal patterns. ACF/PCF of residuals. Ideally, all lags should fall within the confidence intervals, the blue shaded region, indicating no significant autocorrelation. If spikes are present, the model might be missing some information. Histogram and QQ plot. The histogram should approximate a bell shape, and the QQ plot should show points closely following the 45-degree line, indicating normality. While perfect normality isn't always achievable, Significant deviations might point to issues or suggest that a different error distribution might be more appropriate. 11.6 Rolling Forecast Implementation. A static forecast predicts future values once based on a fixed training set. However, in real-world scenarios, new data becomes available, and models need to adapt. A rolling forecast, also known as a walk-forward validation, simulates a real-time forecasting process by iteratively retraining the model or updating its parameters as new data points become available. This provides a more robust and realistic evaluation of the model's performance over time. 1.6.1 Concept of rolling forecasts. The process involves 1. Define an initial training window. 2. Train the model on this window. 3. Forecast the next code snippet steps, e.g., 1 month. 4. Add the actual observed value for that code snippet step to the training window. 5. Retrain the model or update it with the expanded window. 6. Repeat steps 3 to 5 for the entire test set. This approach ensures that the model always uses the most up-to-date information available at each forecasting point, mimicking how a model would be used in a production environment. The problem specifies forecasting 12 months ahead at each step, but for evaluation, it's more common to forecast just one step ahead in a rolling fashion to compare directly with actuals at each point. For this capstone, we will stick to the standard rolling forecast, where we predict one step ahead and then retrain/update. We forecast 12 steps ahead in the final prediction, but for the evaluation of the model on the test set, a one-step rolling forecast is more appropriate to compare against actuals. Download the code on OnePageCode Substack. This loop implements the rolling forecast. 1. Code snippet starts with all training data. 2. In each iteration code snippet, a new code snippet model is instantiated and fitted using the current code snippet. This is crucial for adapting the model. Code snippet generates a one-step ahead forecast. The code snippet prediction is stored. The actual observed value, code snippet, from the code snippet for the current time. Step code snippet is retrieved. Code snippet is appended to code snippet, extending the training window for the next iteration. This simulation gives us a more realistic assessment of model performance than a single static forecast. 11.7 Model Evaluation and Interpretation. The final step is to evaluate the model's performance using appropriate metrics and visualize the results. It's also important to compare against a baseline model to understand if our sophisticated SARIMA model truly adds value. 1.7.1 Choosing an appropriate baseline. A baseline model is a simple forecasting method against which your more complex model's performance can be compared. It helps determine if your model is actually doing better than a naive approach. 4-time series with seasonality. A common baseline is the seasonal naive model, which predicts that the next value will be the same as the value from the previous season. E.g., the prescription count for January next year will be the same as January this year. Download the code on OnePageCode Substack. The code snippet would be used for comparison. For simplicity in this capstone, we'll focus on evaluating our SARIMA model against the actual code snippet directly using common metrics. The code snippet variable is set to ensure it has the same length and aligns with our code snippet list. 1.7.2 Error Metrics. Common error metrics for time series forecasting include mean absolute error, MA, the average of the absolute differences between in predictions and actual values. It's easy to interpret as it's in the same units as the data. Mean squared error, MSE, the average of the square differences. It penalizes larger errors more heavily. Root mean squared error, RMSE, the square root of MSE. It's also in the same units as the data and is widely used. Mean absolute percentage error. Make the average of the absolute percentage errors. Useful for understanding error in relative terms, but sensitive to zero or near zero actual values. Download the code on OnePageCode Substack. This code calculates the key error metrics. Lower values for MAE, RMSE, and MAPE indicate better model performance. The code snippet function is defined manually to handle potential division by zero issues gracefully if actual values could be 0. 1.7.3 Visualizing forecast results. Plotting the actual values against the predicted values for the test set provides an intuitive understanding of the model's performance. Download the code on OnePageCode Substack. This plot visually summarizes the model's performance. We can see how well the green dashed line, forecast, tracks the orange line, actual test data. Any significant deviations consistent under or over forecasting or inability to capture peaks/troughs would be evident here. 1.7.4 Final forecast for future months. Finally, we can use our best performing model to forecast future, unseen months. The problem specifies forecasting 12 months ahead. Download the code on OnePag. The code Substack. In this final step, we retrain the SARIMA model on the entire available dataset, both training and test data. This is a common practice when making final predictions, as it leverages all historical information. We then use code snippet to generate forecasts for the next 12 months. The code snippet are generated using code snippet to create a proper time index for these future predictions, allowing for clear visualization and interpretation. 1.7.5 Real-world implications. The accuracy of these forecasts has significant real-world implications in healthcare. Resource allocation. Accurate predictions help hospitals and clinics allocate staff, beds, and other resources more efficiently to manage patient load related to diabetes. Drug supply chain management. Pharmaceutical companies and pharmacies can optimize inventory levels, reducing waste from overstocking and preventing shortages that could impact patient care. Public health policy. Forecasts can inform public health initiatives, identify potential areas for intervention, and aid in planning for future healthcare demands related to chronic conditions like diabetes. This Capstone project demonstrates an end-to-end time series forecasting workflow, from initial data exploration to model evaluation and future prediction, highlighting the practical utility of these techniques in real-world scenarios. Importing the required libraries and loading the data. The initial step in any data analysis or machine learning project is to set up the environment and load the dataset. This section guides you through the process of importing essential Python libraries and ingesting our time series data into a pandas data frame, preparing it for subsequent analysis and modeling. Setting up the environment. Importing essential libraries. Python's strength in data science lies in its vast ecosystem of specialized libraries. By importing these libraries, we make their functions and tools available for use in our code. It's common practice to import all necessary libraries at the beginning of a script or notebook, even if they aren't used immediately. This provides a clear overview of the project's dependencies and anticipates future needs. We will begin by importing core libraries for data manipulation and visualization. Download the code on OnePageCode Substack. Code snippet, aliased as code snippet. This is the cornerstone library for tabular data manipulation in Python. Its primary data structure, the code snippet, is highly optimized for handling structured data, making it indispensable for tasks like data loading, cleaning, transformation, and analysis. We will use it extensively to manage our time series data. Code snippet, aliased as code snippet, while code snippet builds on code snippet itself provides powerful n-dimensional array objects and a wide range of func. Tie-ins for numerical computations. It's the backbone for many scientific computing tasks in Python, and code snippet data frames are essentially built upon code snippet arrays. Code snippet, aliased as code snippet, this is the foundational plotting library in Python. While code snippet offers a higher-level interface, code snippet provides fine-grained control over plots, allowing for extensive customization. We will use it for visualizing our time series data and model results. Code snippet, aliased as code snippet built on top of code snippet. Code snippet provides a high-level interface for drawing attractive and informative statistical graphics. It simplifies the creation of complex plots, making it easier to explore relationships within your data, which is beneficial for time series analysis to identify patterns or seasonality. Next, we import libraries crucial for statistical modeling, machine learning, and general utility within a time series context. Download the code on one patch code Substack. Code snippet, aliased as code snippet, and code snippet, aliased as code snippet. Code snippet is a powerful library that provides classes and functions for estimating many different statistical models, conducting statistical tests, and exploring data. The code snippet time series analysis submodule is particularly relevant for this project as it contains implementations of various time series models, including SARIMA, which we will use. Code snippet, aliased as code snippet. Code snippet is a collection of scientific computing modules. The code snippet module provides a wide range of probability distributions and statistical functions, useful for hypothesis testing, data analysis, and understanding the statistical properties of our time series. Code snippet. This built-in Python module allows us to control how warning messages are displayed. While warnings often indicate potential issues that should be addressed in a tutorial or specific analysis context, it's sometimes desirable to suppress non-critical warnings for cleaner output. We'll see how to do this shortly. Code snippet. This module implements a number of iterator building blocks, useful for creating efficient loops. In the context of time series modeling, it's often used for generating combinations or permutations of hyperparameters when performing grid searches for optimal model configurations, e.g., for SARIMA code snippet orders. Code snippet. This is part of Python's code snippet module, used for type hinting. While not directly involved in computation, type hints improve code readability and help catch potential errors during development, especially in larger projects. For instance, code snippet indicates a variable can be an integer or a float. Code snippet. The code snippet library provides fast, extensible progress bars for Python loops. When performing computationally intensive tasks like hyperparameter tuning for SARIMA models, a progress bar helps visualize t remaining execution time, enhancing the user experience in a Jupyter Notebook environment. Configuring the environment. Magic commands and warning suppression. Jupyter Notebooks and IPython environments offer special magic commands that provide additional functionality beyond standard Python syntax. We'll use one such command to ensure plots are displayed correctly within the notebook output. We will also configure the warning system. Download the code on one patch code Substack. Code snippet. This is an IPython magic command specific to Jupyter Notebooks and other IPython environments. Its purpose is to ensure that code snippet plots are embedded directly below the code cell that generates them, rather than opening in a separate window. Without this command, your plots might not appear directly in your notebook. Code snippet. This line tells Python's warning system to ignore all warning messages. While useful for creating clean output in tutorials or when you're confident that warnings are benign, it's crucial to understand its implications. In a production environment or during initial development, suppressing warnings can obscure important information about potential issues, deprecations, or unexpected behavior in your code or libraries. Always consider the trade-off between cleaner output and potential loss of diagnostic information. Loading the data set. With our environment set up and configured, the next step is to load our time series dataset. The data for his Capstone Project code snippet is expected to be located in a code snippet folder relative to where your Python script or Jupyter Notebook is being executed. Download the code on one patch code Substack. Code snippet. This line defines a string variable code snippet that holds the location of our dataset. The path code snippet is a relative path, meaning the system looks for a folder named code snippet in the same directory where your script or notebook is running, and then for code snippet inside that folder. If your file is in a different location, you'll need to adjust this path accordingly. Code snippet. This is a fundamental pandas function used to read data from a comma-separated values, CSV, file directly into a pandas data frame. A pandas data frame is a two-dimensional, tabular data structure with labeled axes, rows, and columns. Think of it as a highly flexible spreadsheet or SQL table. It's the primary data structure for almost all data analysis tasks in Python. Code snippet. This block is a robust way to handle a common issue, the file not being found. The code snippet block attempts to execute the code within it, in this case, loading the CSV. If a code snippet occurs during the execution of the code snippet block, meaning the specified CSV file doesn't exist at the given path, the code within the code snippet block is executed. This prints a helpful error message to the user, guiding them on how to resolve the issue rather than crashing the program. This is a crucial best practice for creating user-friendly and resilient code. Other data loading functions. Pandas provides similar functions for various other data sources, such as code snippet for Excel files, code snippet for JSON data, and code snippet for reading data directly from a database using SQL queries. The code snippet function is merely one of many tools for data ingestion. Initial data inspection. After loading the data, it's vital to perform immediate inspection. This helps you verify that the data was loaded correctly, understand its basic structure, identify potential issues like incorrect data types or missing values, and confirm that the dataset matches your expectations. Catching these issues early can save significant time and effort later in the analysis process. Let's start by checking the dimensions of our newly loaded data frame. Download the code on one PageCode Substack. Code snippet. This is an attribute of a Pandas data frame that returns a tuple representing its dimensionality. The first element of the tuple is the number of rows, and the second is the number of columns. For time series data, the number of rows typically corresponds to the number of observations, e.g., months, days, and the number of columns corresponds to the number of variables, e.g., date, drug prescriptions. This gives us a quick overview of the dataset size. While code snippet tells us the size, code snippet gives us a glimpse into the actual data content. Load the code on one PageCode Substack. Code snippet. This method returns the first 5 rows of the data frame by default. It's incredibly useful for a quick visual check to ensure the data has loaded correctly, that column headers are as expected, and that the data types appear consistent with what you anticipate, e.g., dates look like dates, numbers look like numbers. This is your first visual confirmation that the data is structured as expected. For a more comprehensive summary of the data frame structure, including data types and non-null counts, code snippet is invaluable. Download the code on one PageCode Substack. Code snippet. This method prints a concise summary of a data frame. This includes the number of entries, rows, the number of columns, a list of all columns, their non-null count, and their data type, code snippet. This is crucial for time series analysis, as your time index column often needs to be of a date-time type, and your target variable should be numeric. Memory usage. The non-null count is especially important for identifying missing values, which often require specific handling in time series forecasting. Finally, it's often helpful to explicitly inspect the index and column names, particularly when working with time series where the date column might become the index. Download the code on one PageCode Substack. Code snippet. This attribute displays the index, row labels of the data frame. For time series data, this will often be a code S. Snippet after appropriate pre-processing. Initially, it's typically a default integer index. Code snippet. This attribute displays the column labels of the data frame. This helps confirm that your variable names are correct and as expected. By performing these initial inspection steps, we establish a solid foundation for the subsequent data cleaning, pre-processing, and modeling stages of our time series forecasting project. Visualizing the series and its components. Before embarking on any time series forecasting endeavor, it is paramount to thoroughly understand the characteristics of your data. This initial phase, often referred to as exploratory data analysis, EDA, involves visualizing the raw series and, crucially, decomposing it into its underlying components. This process provides invaluable insights into the presence of trends, seasonal patterns, and residual noise, which are essential for selecting and configuring appropriate forecasting models like SARIMA. Plotting the raw time series data. The first step in understanding our time series is to plot the raw data. This allows for an immediate visual inspection of its behavior over time, helping us identify obvious trends, recurring patterns, and any unusual observations or outliers. For our anti-diabetic drug prescription data, we expect to see a general progression over the years and potentially annual fluctuations. We begin by importing the necessary libraries: code snippet for plotting, code snippet for data manipulation, and code snippet for numerical operations. Though for date handling, we'll leverage Panda's built-in capabilities more directly. Download the code on one patch code Substack. This initial block imports our core libraries. We assume that the code snippet data frame containing our time series data, with a datetime index and a column named code snippet, has already been loaded and prepared in the preceding steps. Having a proper datetime index is crucial as it allows code snippet to intelligently format the x-axis with dates. Now, let's create a basic plot of the code snippet series. We'll use code snippet to get explicit code snippet and code snippet objects, which gives us more control over the plot. Download the code on one patch code Substack. Here, code snippet creates a new figure and a single subplot axis on it, specifying the figure size for better readability. We then plot code snippet against code snippet. The code snippet conversion is important if your index is a code snippet, as code snippet typically works better with code snippet for automatic date formatting. The code snippet and code snippet arguments are simple aesthetic choices. After plotting the data, it's good practice to add descriptive labels and a title to make the plot understandable. Download the code on one patch code Substack. These lines add an x-axis label, a y-axis label, and a main title to our plot, making it self-explanatory. Finally, we apply some common code snippet utilities to ensure the date labels on the x-axis are well formatted and legible, especially when dealing with many data points over several years. Download the code on one patch code Substack. The code snippet function automatically adjusts the rotation and alignment of the x-axis labels, which is particularly useful for dates. Code snippet automatically adjusts subplot parameters for a tight layout, preventing labels or titles from overlapping. Code snippet displays the generated plot. Interpreting the raw series plot. Upon viewing the plot, you should observe several key characteristics. Trend. Is there a general upward or downward movement over time? For the antidiabetic drug prescriptions, you'd likely see a clear upward trend, indicating increasing demand or usage over the years. Seasonality. Are there regular, repeating patterns within a fixed period, e.g., annually, quarterly, monthly? You might notice a recurring pattern within each year, such as peaks or troughs at specific times of the year, suggesting annual seasonality in prescription rates. Variance. Does the variability of the series change over time? Does the amplitude of the seasonal pattern appear to increase with the level of the series? Outliers/anomalies. Are there any data points that stand out significantly from the general pattern? These initial observations are crucial for guiding our next steps, particularly in choosing appropriate decomposition methods and preparing for model selection. Time series decomposition, unveiling hidden patterns. While the raw plot gives a general sense of the series, a more rigorous analysis involves decomposing the time series into its fundamental components. 1. Trend component, the long-term progression or direction of the series. It reflects underlying growth, decline, or stability over time. 2. Seasonal component, the regular, repeating pattern of fluctuations within a fixed period, e.g., annual, quarterly, monthly. This pattern is typically consistent in amplitude and frequency. 3. Residual component, or noise/irregular component, what remains after the trend and seasonal components have been removed. This represents the irregular, unpredictable fluctuations in the series. Ideally, residuals should resemble white noise, meaning they are random and show no discernible pattern. Why decompose? Decomposition helps us understand drivers. Is the primary driver of change long-term growth, seasonal demand, or random events? Simplify modeling by understanding and potentially removing, through differencing, trend and seasonality, the remaining series, residuals, becomes easier to model using techniques that assume stationarity. Identify anomalies. Outliers or structural breaks often become more apparent in the residual component. Additive versus multiplicative models. Time series decomposition models can be broadly classified as additive or multiplicative. Additive model, code snippet. The magnitude of seasonal fluctuations does not vary with the level of the series. Suitable when the absolute changes due to seasonality are constant. Multiplicative model, code snippet. The magnitude of seasonal fluctuations increases or decreases with the level of the series. Suitable when the percentage changes due to seasonality are constant. Often, taking the logarithm of a multiplicative series transforms it into an additive one. For prescription data, where the seasonal fluctuation, an S might grow as the overall number of prescriptions increases, a multiplicative model might seem appropriate. However, for robustness, we often use methods like seasonal trend decomposition using LUS, STL. Seasonal trend decomposition using LUS, STL. While simpler decomposition methods like code snippet exist, they have limitations, e.g., they don't handle missing values and can be sensitive to outliers. For more robust analysis, especially in practical applications, seasonal trend decomposition using LUS, STL, is often preferred. Why STL? Robustness to outliers. STL is less sensitive to extreme values in the data compared to classical decomposition methods. Handles varying seasonality. It can handle cases where the seasonal pattern changes gradually over time, though our specific implementation here assumes a fixed period. Flexibility. It allows for independent control over the smoothness of the trend and seasonal components. Any type of seasonality can handle both additive and multiplicative seasonality by applying a log transformation, first for multiplicative, then decomposing, then exponentiating back. How STL works, high-level overview. STL is an iterative procedure that uses LUS, locally estimated scatterplot smoothing, a non-parametric regression method, to estimate the trend and seasonal components. 1. Detrending. The series is initially detrended. 2. Cycle subseries smoothing. For each season, e.g., all January values, all February values. A LUS smooth is applied to extract the seasonal pattern. 3. Deseasonalizing. The series is deseasonalized by subtracting the seasonal component. 4. Trend smoothing. A LUS smooth is applied to the deseasonalized series to estimate the trend. 5. Residual calculation. The residuals are calculated by subtracting the estimated trend and seasonal components from the original series. This process is iterated multiple times, refining the estimates of the trend and seasonal components in each pass until convergence is achieved. Performing STL decomposition and visualization. Now, let's apply STL decomposition to our drug prescription data using code snippet. First, we need to import the code snippet class. Download the code on OnePageCode Substack. This line imports the necessary code snippet function from the code snippet library, which is a powerful tool for time series analysis in Python. Next, we perform the decomposition. A critical parameter for code snippet in any seasonal decomposition is code snippet. Download the code on OnePageCode Substack. Here, code snippet initializes the STL decomposition object. Code snippet. This is our time series data, the number of prescriptions. Code snippet. This is crucial. Since our data is monthly and we expect an annual seasonal pattern, i.e., a pattern that repeats every 12 months, we set the period at 12. If our data were daily with a weekly seasonality, code snippet would be 7. If quarterly with annual seasonality, code snippet would be 4. Code snippet. This makes the LUS procedure more robust to outliers, reducing their influence on the trend and seasonal estimates. The code snippet method then executes the decomposition and returns in code snippet object. This object contains the decomposed components as attributes. Now, we'll plot the results of the decomposition. This usually involves plotting the observed series, trend, seasonal, and residual components in separate subplots, sharing the x-axis for easy comparison. Download the code on OnePageCode Substack. This block sets up a 4-row, 1-column subplot layout using code snippet. The code snippet argument ensures that zooming or panning on one subplot's x-axis also affects the others, making it easy to compare patterns across components over the same time frame. We then plot the code snippet, which is just the original series, on the first subplot and set its label. Next, we plot the extracted trend component. Download the code on one patch code substack. The code snippet attribute holds the long-term trend component. Plotting it helps us clearly see the underlying growth or decline, smoothed out from short-term fluctuations. Then, the seasonal component. Download the code on one patch code substack. The code snippet attribute represents the recurring pattern. This plot helps us understand the typical annual fluctuations, independent of the overall trend. For monthly data, you should see a repeating cycle of 12 points. Finally, the residuals. Download the code on one patch code substack. The code snippet attribute contains the remaining noise or irregular component. This is often the most important plot for diagnostic purposes. To finalize the plot, we apply the same date formatting and layout adjustments as before. Download the code on one patch code substack. Interpreting the decomposed components. Observed plot. This is just a replot of your original data, serving as a reference. Trend plot. You should see a smooth line representing the underlying long-term movement. For the drug prescription data, this will likely be a steadily increasing line, indicating a consistent rise in prescriptions over the years. The slope of this line gives insight into the rate of change. Seasonal plot. This plot shows the repeating pattern within each period, e.g. year. You'll observe distinct peaks and troughs at specific months, consistent across different years. For example, if drug prescriptions peak in winter months and dip in summer, this pattern will be evident here. The amplitude of these seasonal fluctuations can also be observed. Residuals plot. This is what's left after removing the trend and seasonal patterns. Good residuals. Ideally, the residuals should look like white noise, random, unpredictable fluctuations centered around zero, with no discernible patterns, trends, or seasonality. This indicates that the trend and seasonal components have captured most of the predictable variation in the series. B. Add residuals. If the residuals still show patterns, e.g., a remaining trend, uncaptured seasonality, increasing/decreasing variance, or obvious clusters of high/low values, it suggests that the decomposition, or your model assumptions, might not be fully capturing the underlying dynamics. For instance, a remaining trend in residuals could mean the initial trend estimation was too smooth, or a remaining seasonal pattern could indicate a more complex seasonality than a simple fixed code snippet can capture. Large spikes in residuals might indicate outliers or structural breaks in the series that warrant further investigation. Connecting visual insights to SARIMA model selection. The visual insights gained from decomposition directly inform the selection of parameters for time series models like SARIMA, Seasonal Autoregressive Integrated Moving Average. Trend and differencing code snippet parameter. If a clear trend is present in the observed series, and thus in the trend component, it indicates that the series is non-stationary in its mean. To make it stationary, we typically apply differencing. A strong, consistent linear trend often suggests that a first-order differencing code snippet will be necessary. If the trend is more complex, e.g., parabolic, higher orders of differencing might be considered, though this is less common for simple trends. Seasonality and seasonal differencing, code snippet and code snippet parameters. If a distinct seasonal pattern is visible in the observed series and the seasonal component, it indicates the need for seasonal differencing in a SARIMA model. The code snippet used in the STL decomposition, e.g., code snippet for monthly annual seasonality, directly corresponds to the seasonal period code snippet in SARIMA. A strong, consistent seasonal pattern usually implies that a first-order seasonal differencing code snippet will be needed. In summary, if your decomposition shows a clear upward trend and a consistent annual seasonal pattern, you're likely to start your SARIMA model exploration with code snippet, and code snippet. The goal of these differencing steps is to transform the original series into a stationary one, whose residuals should resemble the white noise observed in the decomposition's residual plot. Modeling the data. Forecasting time series data effectively often hinges on a crucial property known as stationarity. A stationary time series is one whose statistical properties, like mean, variance, and autocorrelation, do not change over time. This makes it easier to model and predict, as we can assume that the future will behave similarly to the past. Many time series models, including the seasonal autoregressive integrated moving average, SARIMA, model, assume that the underlying series is stationary. Understanding stationarity. Imagine a time series that constantly increases over time, like the total number of prescriptions. This series has a clear upward trend, meaning its mean is not constant. Or consider a series where the fluctuations become much wider in later periods, indicating non-constant variance. These are examples of non-stationary series. A truly stationary time series exhibits constant mean. The average value of the series remains constant over time. Constant variance. The spread or variability of the data points around the mean remains consistent. Constant autocorrelation structure. The relationship between a data point and its past values, autocorrelation, remains stable over time. Why is stationarity so important for models like SARIMA? Models like SARIMA rely on historical patterns to forecast future values. If the statistical properties of a series are constantly changing, these models struggle to capture stable relationships, leading to inaccurate rate predictions. By transforming a non-stationary series into a stationary one, we stabilize its properties, making it more predictable. Testing for stationarity. The Augmented Dickey-Fuller (ADF) test. While we can visually inspect a time series for signs of non-stationarity, e.g., obvious trends or changing variance, a more rigorous approach involves statistical tests. The Augmented Dickey-Fuller (ADF) test is a widely used statistical test to determine if a unit root is present in a time series, which would indicate non-stationarity. The ADF test works with the following hypotheses. Null hypothesis, $H0 the time series has a unit root and is non-stationary. Alternative hypothesis, $H1 the time series does not have a unit root and is stationary. To interpret the test result, we look at the p-value. If the p-value is less than a chosen significance level, commonly 0.05, we reject the null hypothesis, concluding that the series is stationary. If the p-value is greater than 0.05, we fail to reject the null hypothesis, suggesting the series is non-stationary and needs differencing. Let's begin by performing the ADF test on our original code snippet series, which represents the number of anti-diabetic drug prescriptions. Remember, code snippet was loaded and prepared in previous sections. Download the code on OnePageCode Substack. The code first imports the necessary code snippet function from code snippet and code snippet for potential differencing operations. IT then executes the ADF test on code snippet. The code snippet function returns a tuple containing the ADF statistic, the p-value, the number of lags used, the number of observations used, and critical values. We are primarily interested in the p-value, code snippet. The print statement helps us quickly assess if the original series is stationary. Given the nature of prescription data, likely to have a trend and seasonality, it's highly probable that the original series will be found non-stationary, requiring further steps. Achieving stationarity. Differencing. If the ADF test indicates non-stationarity, we need to apply differencing. Differencing is a transformation technique that involves computing the difference between consecutive observations in a time series. This process helps to remove trends and seasonality, making the series stationary. Non-seasonal differencing, determining code snippet. Non-seasonal differencing involves subtracting the previous observation from the current observation. This effectively removes the trend component from the series by focusing on the changes between time points rather than their absolute values. The code snippet parameter in SARIMA refers to the order of non-seasonal differencing required. Mathematically, a first-order non-seasonal difference is calculated as $y igual a y t-1 Let's apply first-order non-seasonal differencing to our series and retest for stationarity. Download the code on one patch code Substack. Here, each snippet calculates the first difference. The resulting array is then converted into a pandas series, aligning its index with the original series, shifted by one period. Visualizing this series is crucial. You should observe that the overall trend present in the original series has largely been removed, and the series now fluctuates around a more constant mean, often 0. Now, let's perform the ADF test on this different series. Download the code on one patch code Substack. After this step, if the p-value is less than 0.05, we found our non-seasonal differencing order code snippet. If not, it means even after removing the linear trend, the series still exhibits non-stationarity, often due to seasonality. Seasonal differencing, determining code snippet and code snippet. Seasonal differencing accounts for the seasonal patterns in the data. It involves subtracting an observation from the observation at the same period in the previous season. The code snippet parameter in SARIMA refers to the order of seasonal differencing, and code snippet is the number of periods in a season. For our anti-diabetic drug prescriptions data, which is monthly, the seasonal period code snippet is 12. This means we compare the current month's value to the value from the same month in the previous year. Mathematically, a first-order seasonal difference with period code snippet is calculated as $YT equals y $TM, where $Y is the already non-seasonally different series. We will apply seasonal differencing to the series that was already non-seasonally differenced. This is a common practice. First remove the trend, then remove the seasonality. Download the code on one patch code Substack. The code snippet line performs the seasonal differencing. Notice how the index of the code snippet is adjusted to account for the code snippet observations lost during this step. The visualization should now show a series that fluctuates around 0 with no apparent trend or repeating seasonal patterns. It should look more like white noise. Finally, we perform the ADF test on this doubly different series. Download the code on one patch code Substack. After these steps, if the p-value is less than 0.05, we have successfully achieved stationarity. The values code snippet from the first non-seasonal differencing step and code snippet from the first seasonal differencing step are now determined. The seasonal period code snippet is derived directly from a monthly frequency of our data. Overdifferencing, a pitfall to avoid. While differencing is a powerful tool, it's possible to overdifference a time series. Overdifferencing introduces unnecessary noise and complexity into the series, which can make it harder for the model to identify patterns and lead to less accurate forecasts. Signs of overdifferencing include an ADF test p-value that is significantly lower than 0.05, e.g., extremely small, like 0.000. The different series showing very high volatility O. Are a clear negative autocorrelation at lag 1 for non-seasonal or lag code snippet for seasonal. The different series looking like pure white noise, but with an unnecessarily high variance. Typically, code snippet and code snippet values of 0, 1, or sometimes 2 are sufficient. Rarely do time series require more than 2 orders of differencing for either non-seasonal or seasonal components. Always aim for the minimum order of differencing that achieves stationarity. Storing the final difference series. For subsequent modeling steps, it's good practice to store the final, stationary series in a well-named variable or even as a new column in your data frame. This ensures that the transformed data is readily available for fitting the SARIMA model. Download the code on one patch code Substack. This code snippet is now ready for the next phase of SARIMA model building. Identifying the AR, P, and Q orders by analyzing its autocorrelation function, ACF, and partial autocorrelation function, PACF plots. The code snippet, and code snippet values determined in this section will directly become part of our SARIMA model parameters, specifically in the SARIMA notation, P, D, Q. Modeling the data, parameter optimization. After understanding the components of our time series and ensuring its stationarity through appropriate differencing, the next critical step in building a SARIMA model is to identify the optimal parameters $P, D, Q, P, D, Q as $. This process is often referred to as hyperparameter optimization or tuning. For SARIMA models, this involves systematically searching for the best combination of non-seasonal autoregressive P, differencing D, and moving average Q orders, as well as their seasonal counterparts P, D, Q, and the seasonal period S. While initial insights into code snippet and code snippet can be gained from differencing and visual inspection, and code snippet is determined by the data's inherent seasonality, e.g., 12 from monthly data, code snippet, code snippet, code snippet, and code snippet require a more systematic approach. A common and robust method for this is a grid search, where we define a range of plausible values for each parameter and then evaluate every possible combination. To determine which combination of parameters yields the best model, we rely on information criteria. The Augmented Information Criterion, AIC, is widely used for this purpose. AIC estimates the relative quality of statistical models for a given set of data. It provides a means for model selection. Given a collection of models, AIC estimates the quality of each model relative to each of the other models. A key feature of AIC is that IT penalizes models for having more parameters, thereby encouraging simpler models that still provide a good fit to the data. This balances the goodness of fit with the complexity of the model, helping to prevent overfitting. A lower AIC value generally indicates a better model. While AIC is a popular choice, other criteria like the Bayesian Information Criterion, BEC, also exist, which penalizes complexity more heavily than AIC. The choice between AIC and BIC often depends on the specific goals and characteristics of the dataset. For this analysis, we will focus on minimizing AIC. Data splitting from model evaluation. Before optimizing our model, it's crucial to split our time series data into training and testing sets. This allows us to train the model on a portion of the data and then evaluate its performance on unseen data, simulating real-world forecasting scenarios. Unlike cross-validation in traditional machine learning, time series data requires a chronological split to preserve the temporal order of observations. We train on an earlier segment of the data and test on a later segment. In our scenario, we will use the first 168 months, 14 years, for training and reserve the remaining 36 months, 3 years, for testing. This split ensures that our model learns from historical patterns and is then evaluated on genuinely future data. Download the code on OnePageCode Substack. The code above performs a standard chronological split of the time series. Code snippet contains each initial segment of the data, which the SARIMA model will use to learn patterns and relationships. Code snippet holds the subsequent segment, representing future data that the model has not seen during training. This clear separation is fundamental for robust model evaluation, preventing data leakage and providing a realistic assessment of forecasting accuracy. Defining the SARIMA parameter search space. The core of our grid search involves defining the ranges for the non-seasonal code snippet and code snippet orders, and the seasonal code snippet and code snippet orders. The code snippet, non-seasonal differencing, and code snippet, seasonal differencing. Orders are typically determined from the stationarity analysis performed earlier, e.g., from ACF/PACF plots or statistical tests like ADF. The seasonal period code snippet is fixed based on the data's frequency, e.g., code snippet for monthly data. We use Python's code snippet to efficiently generate all possible combinations of these parameters within our defined ranges. This function is invaluable for creating Cartesian products, which is exactly what a grid search requires. Download the code on OnePageCode Substack. Here, we establish the boundaries for our parameter search. Code snippet, code snippet, code snippet, and code snippet define the potential values for the AR, MA, seasonal AR, and seasonal MA components, respectively. The code snippet and code snippet values are held constant, as they are typically derived from the data's inherent properties and stationarity requirements rather than being part of the grid search for optimization. Code snippet then systematically creates every permutation of these orders, forming the grid that our optimization function will traverse. Automating SARIMA's model fitting with code snippet. Fitting multiple SARIMA models manually for each parameter combination is tedious and error-prone. To streamline this process, we create a reusable Python function, code snippet. This function encapsulates the logic for iterating through the parameter grid, attempting to fit a SARIMA model for each combination, capturing its AIC, and handling potential errors during the fitting process. Function definition and initialization. The code snippet function takes the endogenous variable, code snippet, an optional exogenous variable, code snippet, the list of parameter orders, and the fixed differencing and seasonal period values. It initializes a list to store results. Download the code on one patch code Substack. This initial part of the code snippet function defines its signature, including type hints for clarity and maintainability. It specifies the inputs required for the optimization process and what type of output, a pandas data frame, it will return. The code snippet list is initialized to collect the AIC and parameter tuple for each successful model fit, looping through parameters and model fitting. The core of the function is a loop that iterates through each code snippet combination generated by code snippet. Inside the loop, a code snippet model is instantiated and then fitted to the training data. Download the code on one patch code Substack. Within this loop, for each parameter combination, a code snippet model is constructed. Code snippet is our training data, code snippet. Code snippet is passed because, in this specific SARIMA context, we are not including any external explanatory variables. If we had additional features that could influence our time series, e.g., economic indicators, weather data, they would be passed here. Code snippet correctly maps the code snippet and code snippet from our code snippet tuple with the fixed code snippet. Code snippet does the same for code snippet, code snippet, code snippet, and code snippet. Code snippet and code snippet are set to code snippet to allow code snippet to attempt fitting even if the initial parameters might violate these conditions. This can be useful in a grid search where some combinations might be borderline. Code snippet is a crucial parameter. When code snippet and code snippet are specified in the code snippet and code snippet tuples, code snippet automatically applies differencing internally. Setting code snippet ensures that the model uses the full data series and applies the specified differencing during the model specification, rather than expecting pre-difference data or applying a simpler differencing scheme. If this were code snip, pet and code snippet or code snippet were non-zero, code snippet would attempt to apply differencing again to the input data, which is usually not desired when code snippet and code snippet are part of the model order. Code snippet is passed to the code snippet method to suppress the detailed optimization output that code snippet prints during the fitting process. This keeps the console clean, especially when fitting hundreds of models. Robust error handling. The code snippet block is vital for the robustness of our grid search. Time series model fitting, especially for complex models like SARIMA with various parameter combinations, can sometimes fail. This can happen due to numerical instability, convergence issues, or invalid parameter combinations. Download the code on one patch code Substack. If an error occurs during code snippet, the code snippet block catches it. The code snippet statement then immediately skips the rest of the current loop iteration and moves to the next parameter combination. Without this, a single failed model fit could terminate the entire optimization process, forcing you to manually debug and restart. This makes the grid search much more resilient and automated. Collecting and returning results. After iterating through all combinations, the collected results are transformed into a pandas data frame, sorted by AIC to easily identify the best performing model. Download the code on one patch code Substack. Finally, the code snippet list, which contain tuples of code snippet, is converted into a pandas data frame. This data frame is then sorted by the code snippet column in ascending order. The code snippet command cleans up the data frame's index after sorting, ensuring a clean, sequential index. The sorted data frame, with the best models, lowest AIC, at the top, is then returned, executing the SARIMA optimization. Now that the code snippet function is defined, we can execute it with our training data and the generated list of parameter combinations. The code snippet wrapper around the loop will provide a visual progress bar, which is very helpful for long-running computations. Download the code on one patch code Substack. This single line of code initiates the extensive grid search. The code snippet function will now systematically fit a SARIMA model for each of the 36 3x3x2x2 parameter combinations, record their AIC, and handle any fitting errors. The code snippet progress bar will update in real time, giving an estimate of the remaining time for the operation, interpreting results, and identifying the optimal model. Once the optimization process is complete, the code snippet data frame will contain all the tested parameter combinations and their corresponding AIC values, sorted from lowest to highest. The model with the lowest AIC is considered the optimal one within our defined search space. Download the code on one patch code Substack. The output of code snippet will show the top-performing models. The first row of this data frame represents the optimal SARIMA model, as it has the lowest AIC. We explicitly extract and print the code snippet tuple and its code snippet value for clarity. This model is now the champion candidate from our grid search and will be used for subsequent forecasting and evaluation, instantiating the final optimal SARIMA model. With the optimal parameters identified, the next logical step is to instantiate the code snippet model using these best parameters. This model can then be used for forecasting on the test set and further analysis. Download the code on one patch code Substack. This code block takes the code snippet, e.g., code snippet, extract it from our results, unpacks it into code snippet, code snippet, code snippet, and code snippet, and then instantiates and fits a new code snippet model using these specific parameters. This code snippet object is now the trained model ready for forecasting. Its code snippet method provides detailed statistical output, including coefficients, standard errors, p-values, and various information criteria, offering deeper insights into the fitted model's characteristics, computational considerations, and alternatives. While grid search is a straightforward and effective method for hyperparameter optimization, it has a significant drawback: computational cost. As the number of parameters and the range of values for each parameter increase, the number of combinations grows exponentially. For instance, if we add another parameter w, if 3 possible values, the total number of models to fit triples. This can quickly become computationally prohibitive for large datasets or extensive search spaces. For scenarios where grid search is too slow, alternative optimization techniques exist. Randomized search. Instead of evaluating every combination, randomized search samples a fixed number of parameter combination from the defined search space. While it doesn't guarantee finding the absolute best combination, it often finds a very good combination much faster than a full grid search, especially in high-dimensional spaces. Bayesian optimization. This is a more sophisticated technique that builds a probabilistic model of the objective function, e.g., AIC, and uses it to select the most promising parameters to evaluate next. It aims to minimize the number of objective function evaluations, making it highly efficient for costly evaluations like model fitting. Tree-structured Parson estimator, TPE, a popular algorithm used in libraries like CodeSnippet. TPE is a form of Bayesian optimization that iteratively models the probability of parameters given good performance and the probability of parameters given bad performance. For the purpose of this tutorial, grid search provides a clear and intuitive understanding of parameter optimization. However, being aware of these more advanced methods is crucial for real-world applications with larger or more complex models. Comparison: automated grid search versus manual CF/PACF analysis. Historically, SARIMA parameters were often determined through a painstaking manual process involving the inspection of autocorrelation function, ACF, and partial autocorrelation function, PACF plots of the different series. Manual ACF/PACF analysis. Pros. Provides deep intuition about the series' underlying structure, AR versus MA, seasonal versus non-seasonal patterns. Can quickly rule out many parameter combinations if patterns are clear. Cons. Subjective, requires significant experience and interpretation skills. Can be ambiguous, especially with mixed ARMA processes or complex seasonality. Time-consuming for multiple candidate models. Does not directly optimize for a specific criterion like AIC. Automated grid search. Pros. Objective and systematic. Guarantees finding the optimal combination within the defined search space based on a chosen criterion, e.g., lowest AIC. Reduces human error and subjective bias. Easily scalable, computationally, if resources allow. Cons. Computationally intensive, especially for wide parameter ranges. Provides less direct intuition about the series structure compared to manual plots. Relies on the quality of the chosen search space. If the optimal parameters lie outside the defined ranges, they won't be found. In practice, a hybrid approach is often best. Use ACF/PACF plots to guide the initial code snippet and code snippet values and to narrow down the plausible ranges for code snippet, code snippet, and code snippet. Then employ a grid search or a more advanced optimization technique within those refined ranges to find the precise optimal values based on AIC or BIC. Modeling the data, residual analysis, and validation. After selecting optimal parameters for a SARIMA model, the crucial next step is to validate its performance. This involves examining the model's residuals, the differences between the observed values and the values predicted by the model. A well-fitted time series model should leave behind residuals that are essentially white noise. The importance of residual analysis. Residuals are what remains of the original time series after the model has captured all the systematic patterns, trends, and seasonality. If a model is correctly specified and has effectively extracted all the predictable information from the data, the residuals should exhibit characteristics of white noise. What is white noise? A white noise process is a sequence of random variables that are 1. Independent and identically distributed, i.e. each residual value is independent of all previous residual values. There's no pattern or correlation left to exploit. 2. Zero mean. On average, the residuals should fluctuate around 0. 3. Constant variance. The spread of the residuals should be consistent over time. Homoscedasticity. Why white noise residuals are desirable. When residuals are white noise, it signifies that all systematic information captured. The model has successfully identified and accounted for all the underlying patterns, trends, and seasonal components in the time series. There's no predictable information left in the errors. Optimal. Forecasting. Any forecast errors will be purely random and unpredictable, meaning the model is as good as it can get given the available data. If there were remaining patterns in the residuals, the model would be systematically biased, leading to inaccurate forecasts and unreliable confidence intervals. Reliable confidence intervals. The uncertainty estimates, confidence intervals, around your forecast will be accurate, as they correctly reflect only the random error. If residuals are correlated, your confidence intervals will be too narrow, giving a false sense of precision. Consequences of non-white noise residuals. If your model's residuals are not white noise, e.g., they show autocorrelation, non-constant variance, or a non-normal distribution, it implies that model misspecification. Your SARIMA model has not fully captured the underlying structure of the time series. There's still predictable information lurking in the errors. Biased forecasts. The forecast generated by such a model will likely be systematically off, consistently over or underpredicting. Inaccurate uncertainty. Confidence intervals will be misleading, potentially leading to poor decision-making in real-world applications like inventory management, resource allocation, or financial risk assessment. Therefore, validating residuals is a critical step to ensure the reliability and trustworthiness of your forecasting model before deployment. Fitting the SARIMA model. Before we can analyze the residuals, we need to fit the SARIMA model with the parameters determined in the previous optimization step. Let's assume our previous analysis concluded that code snippet and code snippet were the optimal parameters for our training data. We'll use the code snippet class from code snippet to define and fit our model. Download the code on one patch code substack. This code snippet first imports the necessary libraries and, for a self-contained example, creates a dummy code snippet dataset. In your actual project, code snippet would be your pre-processed time series data. We then instantiate the code snippet model with our chosen code snippet and code snippet parameters. The code snippet argument is crucial. It tells code snippet that we have explicitly handled the differencing, the code snippet and code snippet components, within our code snippet and code snippet tuples, rather than letting the model automatically determine it. Now, we fit the model to the training data. The code snippet method performs the estimation of the model coefficients. Download the code on one patch code substack. The code snippet line fits the model. Code snippet is a common practice to prevent the optimization routine from printing verbose convergence information, which can clutter your output, especially when fitting many models. After fitting, we print the code snippet of the fitted model, which provides a wealth of information about the estimated parameters, standard errors, p-values, and various info. Remation criteria, like AIC, BC, which we used in previous sections for parameter optimization. Qualitative residual analysis, diagnostic plots. The code snippet library provides a convenient method, code snippet, to visually inspect the residuals of a fitted model. This method generates 4 subplots that offer different perspectives on the residuals characteristics. Before looking at the plots, let's understand what each plot represents and what characteristics we expect for white noise residuals. 1. Standardized residuals. Purpose shows the time series of the residuals, scaled by their standard deviation. Ideal appearance should fluctuate randomly around 0, with no discernible pattern, trend, or seasonality. The variance should appear constant over time, homoscedasticity. Large spikes or systematic changes in variance suggest issues. What to look for: non-ideal trends, cycles, seasonality, or increasing/decreasing variance, heteroscedasticity, indicate that the model has not captured all the information. 2. Histogramme plus KDU estimate. Purpose displays the distribution of the residuals. A kernel density estimate, KD, plot is overlaid to smooth the histogram and provide a continuous estimate of the probability density function. Ideal appearance should approximate a normal distribution centered around 0. What to look for: non-ideal skewness, asymmetric distribution, kurtosis, too peaked or too flat, or multiple peaks suggest that the residuals are not normally distributed, which can affect the validity of confidence intervals and hypothesis tests. 3. Normal QQ plot. Purpose compares the quantiles of the residuals distribution to the quantiles of a theoretical normal distribution. Ideal appearance. The points should closely follow a straight diagonal line. What to look for: non-ideal deviation from the straight line, e.g. S-shapes, tails curving away, indicate departures from normality, such as heavy tails, more outliers than expected, or skewness. 4. Correlogram, ACF. Purpose shows the autocorrelation function, ACF, of the residuals. Autocorrelation measures the correlation of a time series with a lagged version of itself. Ideal appearance. All bars should fall within the shaded blue confidence band, typically 95% confidence interval, indicating that correlations are not statistically significant. Only the lag 0 bar should be at 1.0. A series is perfectly correlated with itself at lag 0. What to look for: non-ideal, any significant spikes outside the confidence band at lags greater than 0 indicate remaining autocorrelation in the residuals. This is a strong sign that the model has not captured all the serial dependencies in the data. Now let's generate these diagnostic plots for our fitted model. Download the code on one patch code substack. This single line of code is powerful. It generates all 4 plots discussed above, providing a comprehensive visual assessment of the residuals. Code snip. PET and code snippet are used for better presentation, ensuring the main title is visible and subplots don't overlap. Interpreting the plots, ideal scenario. For our model to be considered well-fitted, we would ideally observe standardized residuals, a random scatter of points around zero with no visible patterns or changes in spread. Histogram plus KD estimate, a bell-shaped curve, symmetric around zero, resembling a normal distribution. Normal QQ plot, all points lying very close to the diagonal line. Parallelogram, ACF, no significant spikes outside the blue-shaded region at any lag greater than zero. If these conditions are met, it suggests that the model has successfully captured the underlying structure of the time series, and the remaining errors are random. You can also save this plot for documentation or reporting purposes. Download the code on one patch code Substack. This code block is similar to the previous one, but instead of calling code snippet, it calls code snippet to save the plot to a specified file. Code snippet is then used to close the figure and free up memory, which is good practice when generating many plots programmatically. Quantitative residual analysis, the Ljung box test. While diagnostic plots provide a good visual assessment, statistical tests offer a more objective and quantitative way to determine if residuals are white noise. The Ljung box test is a widely used statistical test for checking if there is significant autocorrelation I. An A-time series. Hypotheses of the Ljung box test. Null hypothesis, $H0, the residuals are independently distributed, i.e., there is no autocorrelation up to a specified number of lags. This is what we want for a well-fitted model. Alternative hypothesis, $H1, the residuals are not independently distributed, i.e., there is significant autocorrelation up to a specified number of lags. Interpreting the p-value. The Ljung box test calculates a p-value for each specified lag. If the p-value significance level, alpha, typically 0.05, we fail to reject the null hypothesis. This means there is not enough evidence to conclude that the residuals are autocorrelated at that lag. This is the desired outcome. If the p-value equals significance level, alpha, we reject the null hypothesis. This indicates that there is significant autocorrelation in the residuals at that lag, implying the model has not captured all the patterns. First, we need to extract the residuals from our fitted model. The residuals are stored as an attribute of the code snippet object. Download the code on one patch code Substack. The code snippet attribute directly gives us the time series of residuals, which is a pandas series. Next, we apply the code snippet function from code snippet. This function takes the residuals and a list of lags at which to test for autocorrelation. Download the code on one patch code Substack. Here, code snippet computes the Ljung box statistic and its corresponding p-value for each specified lag. We've chosen to test up to lag 10 using code snippet. The output is a pandas data frame, where the code snippet column contains the p-values we are interested in. To conclude whether our model's residuals resemble white noise, we need to check if all the p-values from the Ljung box test are above our chosen significance level. A common significance level, alpha, for this test is 0.05. Download the code on one patch code Substack. This programmatic check provides a clear conclusion based on the statistical test. If code snippet is code snippet, it supports the qualitative assessment that the residuals are white noise, and your model is likely well specified. If code snippet, it indicates that some form of autocorrelation remains in the residuals, signaling that the model could be improved. What if residuals are not white noise? Troubleshooting. If your qualitative and quantitative residual analyses indicate that your model's residuals are not white noise, it means your current SARIMA model is likely misspecified. This is a common scenario in time series modeling, and it requires a systematic approach to diagnose and resolve the issue. Here's a guide on what to do next. 1. Revisit differencing DD. Issue. Residuals show a trend or strong seasonality, especially in the parallelogram, large spikes at seasonal lags. Action. This often indicates insufficient differencing. Review your initial stationarity analysis. ACF/PACF plots of the raw data or prior difference data. If a trend is still present, you might need an additional non-seasonal difference code snippet. If seasonality is still prominent, an additional seasonal difference code snippet might be required. Be cautious not to overdifference, as this can introduce negative autocorrelation and make the model less interpretable. Overdifferencing often appears as significant negative spikes in the ACF at lag 1. 2. Reoptimize model orders PQPQ. Issue: significant spikes in the residual correlogram, ACF, or partial correlogram, PACF, at specific lags. Action: this means the ARIMA components, code snippet, code snippet, code snippet, code snippet, might not be correctly specified. If a spike at lag code snippet in the residual ACF is significant, consider increasing code snippet or code snippet for seasonal lags. If a spike at lag code snippet in the residual PACF is significant, consider increasing code snippet or code snippet for seasonal lags. You might need to rerun your parameter optimization grid search, perhaps expanding the range of values for code snippet, code snippet, code snippet, code snippet around the current optimal values. Pay close attention to the AIC/BC values during this process. 3. Consider data transformations. Issue: non-constant variance heteroscedasticity. In the standardized residuals plot, e.g., the spread of residuals increases over time, or non-normal distribution of residuals. Action: a Box-Cox transformation, or simply a log transformation, can often stabilize the variance of the series, making it more amenable to SARIMA modeling. Apply the transformation to the original series before differencing and modeling. Remember to inverse transform your forecasts back to the original scale. 4. Explore exogenous variables, SARIMAX. Issue: if the model still struggles to capture patterns despite exhaustive SARIMA parameter tuning, there might be external factors influencing your time series. Action: consider adding relevant external variables, e.g., economic indicators, holidays, marketing campaigns, weather data, to your model. The code snippet model in code snippet supports exogenous variables through its code snippet parameter. This transforms your model into a SARIMAX model. 5. Switch to different model classes. Issue: despite all efforts, SARIMA might simply not be the best fit for your data. Action: explore alternative time series models. Exponential smoothing models, ETS, good for data with clear trend and seasonality, but without a strong need for differencing. Profit: Facebook user-friendly for forecasting with multiple seasonality and holidays. Machine learning models, for more complex, nonlinear relationships, models like gradient boosting, XGBoost, LightGBM, or neural networks, LSTMs, can be employed, often with lag features. Residual analysis is an iterative process. It helps you diagnose model deficiencies and guides you towards improvements. By Systematica, LLY addressing issues identified through diagnostic plots and statistical tests, you can build more robust and reliable forecasting models. We have meticulously prepared our time series data, identified its components, ensured stationarity, and optimized our SARIMA model's parameters. We also validated the model's residuals to ensure it captures the underlying patterns effectively. The next crucial step is to evaluate its actual forecasting prowess. This involves generating predictions on unseen data and quantifying how well those predictions align with reality. 1. The concept of rolling forecasts, walk-forward validation. When evaluating a time series forecasting model, a simple train test split, where the model is trained once on an initial segment and then predicts the entire future test set, can be misleading. In real-world scenarios, new data becomes available over time, and a robust model should ideally incorporate this new information to refine its future predictions. This is where rolling forecasts, also known as walk-forward validation, become indispensable. Why rolling forecasts? Rolling forecasts simulate a real-time forecasting environment. Instead of training a model once and predicting a long future horizon, the process involves 1. Initial training. Train the model on an initial segment of the historical data. 2. One-step ahead prediction. Generate a forecast for the very next time step. 3. Observation and retrain. The actual value for that time step becomes available. The model is then retrained, incorporating this new observed data point into its training set. 4. Repeat. Steps 2 and 3 are repeated, rolling the training window forward one step at a time. This approach offers several advantages. Adaptive learning. The model continuously learns from the most recent observations, adapting to subtle shifts in trend or seasonality. Robust evaluation. It provides a more realistic assessment of how the model would perform in a live production environment where new data constantly arrives. Reduced overfitting. By refitting on slightly different data windows, it helps prevent overfitting to a single static training set. Realistic error measurement. Error metrics calculated from rolling forecasts are typically more indicative of true out-of-sample performance. Computational considerations. It's important to acknowledge that refitting the SARIMA model in each iteration of a rolling forecast can be computationally intensive, especially for very long test sets or complex models. Each code snippet operation involves numerical optimization, which can take time. For high-frequency data or very long forecast horizons, strategies like refitting less frequently, e.g., every month instead of every day, or using simpler, less computationally demanding models for rolling forecasts might be necessary. However, for typical monthly or weekly data over a moderate test period, this approach is highly recommended for robust evaluation. 2. Defining performance metrics. To quantitatively evaluate our model, we need appropriate metrics. While many exist, e.g., mean absolute error, ME, root mean squared error, RMSE, mean squared error, MSE. The mean absolute percentage error, MAPE, is particularly intuitive for business stakeholders as it expresses accuracy as a percentage. Mean absolute percentage error, MAPE. MAPE calculates the average absolute percentage difference between the actual values and the forecasted values. It is defined as $MAP equals \frac 1 in backslash some t equals 1 current backslash left backslash frac actual forecast actual backslash right backslash times 100 backslash percent dollar, where $actual dollar is the actual value at time $t dollar. Dollar forecast dollar is the forecasted value at time $t dollar. Dollar and dollar is the number of forecasts. Advantages and disadvantages of MAPE. Advantages. Interpretability. Easy to understand for non-technical audiences, e.g., our forecast is off by an average of 5%. Scale independent. Expressed as a percentage, it allows for comparison across different datasets or series with varying scales. Disadvantages. Undefined for zero actuals. If an actual value, $actual dollar, is 0, MAPE becomes undefined due to division by 0. This is a significant drawback if your data can genuinely have 0 values, e.g., sales of a product that occasionally sells nothing. Bias towards underforecasting. It penalizes positive errors, overforecasting, more heavily than negative errors, underforecasting, when the actual value is small. Sensitive to small actual values. Even a small absolute error can result in a very large percentage error if the actual value is close to 0. Given these side rations, it's often good practice to report other metrics alongside MAPE, such as MAE and RMSE, to provide a more holistic view of model performance. MAE and RMSE are scale-dependent, but are well-defined for all actual values and have different sensitivities to large errors. RMSE penalizes large errors more heavily due to squaring. Let's define a Python function to calculate MAPE. Download the code on OnePageCode Substack. This code snippet function takes 2 arguments: code snippet, the actual values, and code snippet, the predicted values. It converts them to number py arrays for efficient calculation. A crucial aspect is handling cases where code snippet might be 0 to prevent division by 0 errors, which would result in code snippet or code snippet. Here, we filter out such instances. 4-time series like sales or demand, actuals are rarely exactly zero, but if they are, consider alternative metrics like ME or RMSE or a small epsilon to avoid division by zero issues. 3. Implementing the rolling forecast function. Now, let's build the core function for generating rolling forecasts. This function will be flexible enough to handle both our sophisticated SARIMA model and a simpler baseline model. The naive, seasonal baseline. To properly assess our SARIMA model's performance, we need a baseline. A common and intuitive baseline for seasonal data is the naive seasonal forecast. This method simply predicts that the value for the next period will be the same as the val. UE from the same period in the previous season. For example, if we're forecasting monthly data with a seasonality of 12 months, the naive seasonal forecast for January 2024 would be the actual value from January 2023. This baseline is important because simplicity, it's easy to understand and implement, serving as a low-bar benchmark. If a complex model cannot outperform this simple baseline, its complexity might not be justified, suggesting that a simpler approach could be more cost-effective. Intuitive, it captures the strong seasonal patterns often present in time series data, making it a surprisingly strong contender for many seasonal series. Let's define the code snippet function. Download the code on OnePageCode Substack. Explanation of code snippet function. Parameters. The function takes the data frame code snippet, initial training data length in terms of observations. Code snippet, how many steps to predict forward at each iteration, typically 1 for walk forward. Code snippet, SARIMA or naive seasonal, and SARIMA code snippet and code snippet tuples. Looping mechanism. Code snippet. This loop is the core of the rolling forecast. In each iteration code snippet, it dynamically expands the training data by 1 observation, code snippet. The loop range code snippet ensures that we always have enough future data points to make a prediction for the specified code snippet from the current training window. Naive seasonal, code snippet. If code snippet is code snippet, it calculates the forecast by simply taking the value from code snippet periods ago in the code snippet. Code snippet is extracted from the code snippet. Error handling is included for cases where there isn't enough historical data for a full season. SARIMA method, code snippet. Model instantiation and code snippet. We instantiate code snippet with the code snippet. The parameter code snippet is critical. It tells code snippet not to automatically apply a simple difference to the input data before model fitting, even if code snippet or code snippet are non-zero in your code snippet or code snippet. This is important for consistency. If you already manually differenced your data in a previous step, e.g., to achieve stationarity, as often recommended for unit root tests, setting code snippet prevents code snippet from redifferencing an already different series. If your code snippet or code snippet includes non-zero code snippet or code snippet components, code snippet will apply the appropriate differencing internally within its state space framework, which is generally more robust than code snippet. Code snippet, code snippet. These are set to code snippet because the differencing parameters code snippet in the code snippet and code snippet tuples handle stationarity and invertibility internally within the SARIMAX model's state space formulation. Forcing them to code snippet might lead to issues if the model is all read. Why correctly specified with differencing? Code snippet. The model is refitted in each iteration. Code snippet suppresses the optimization output, keeping the console clean. This is the most computationally intensive part of the rolling forecast. Code snippet. This method generates the forecast. The code snippet and code snippet indices refer to the positions in the original data frame, code snippet. So, code snippet means the prediction begins at the index corresponding to the first element of the test set for the current iteration. Code snippet indicates the last index to predict. For a one-step-ahead forecast, code snippet would simply be code snippet. Error handling, code snippet. A code snippet block is included to gracefully handle potential code snippet fitting errors, e.g., convergence issues, singular matrices. If an error occurs, code snippet values are appended to the predictions, preventing the entire process from crashing. In a production system, you might log these errors for further investigation. Code snippet appends the generated forecast to the overall code snippet list. Return value. The function returns a pandas series of predictions with an index aligned to the corresponding actual values in the test set. 4. Executing forecasts and storing results. With our code snippet and code snippet functions defined, we can now apply them to our data. We'll first define our training and testing periods, then run the rolling forecast for both the naive seasonal baseline and our optimized SARIMA model. Download the code on one PageCode Substack. Here, we set up our SARIMA parameters, which would come from the optimization step, and define the initial code snippet and code snippet. Code snippet determines the size of the initial training window. The code snippet is created, indexed by the test set dates, and populated with the actual values from the test set, ready to receive predictions. Download the code on one PageCode Substack. We call code snippet twice, once for the naive seasonal method and once for the SARIMA method, passing the appropriate parameters. The results are stored in code snippet. Note the print statements indicating progress, especially for SARIMA, as it can be time-consuming due to repeated model fitting. 5. Quantitative performance evaluation. Now that we have our predictions, we can calculate the performance metrics. We will focus on MAPE as our primary metric, but also calculate MAE and RMSE for a more comprehensive view. Download the code on one PageCode Substack. We use code snippet on code snippet to ensure that our metric calculations are performed only on periods where both actuals and predictions are available for both models. This prevents code snippet values from distorting the metrics. We then calculate MAPE using our custom function and MT/RMSE using code snippet. The results are printed clearly, allowing for direct comparison. Finally, a simple conditional statement determ ns and prints the champion model based on MAPE. Interpreting MAPE values. A MAPE of, for example, 5% means that, on average, the model's predictions deviate by 5% from the actual values. Lower MAPE values indicate higher accuracy. For business applications, this translates directly. If you're forecasting sales, a 5% MAPE means your sales forecasts are typically within 5% of what actually gets sold, which can significantly impact inventory management or production planning. 6. Visualizing forecast performance. Visualizations are critical for understanding model performance beyond just numbers. We'll create two types of plots. 1. Time series plot, to visually compare actual values against both forecasted series over the test period. 2. Bar chart of error metrics, to provide a quick visual comparison of the calculated MAPE and other metrics for each model. Time series forecast visualization. Download the code on one PageCode Substack. Explanation of time series plot. Code snippet creates a matplotlib figure and a single subplot, acts as object for plotting. Plotting data. The historical training data, showing the last few periods for context, actual test values, naive seasonal forecasts, and SARIMA forecasts are plotted with distinct colors and line styles for easy differentiation. Code snippet. This function controls the range of the x-axis. Here, we're setting it to show some of the training data. Last two seasonal periods, code snippet, leading up to the test set, and then the entire test set. Using datetime objects directly as limits for a datetime x-axis is convenient. Code snippet. This function draws a vertical span, a shaded rectangle, across the x-axis. We use it to visually highlight the test region, making it clear which part of the plot represents actual forecasting performance. The code snippet and code snippet arguments should correspond to the x-axis values, dates in this case, where the span begins and ends. Labels, title, legend, grid, standard plotting elements for clarity. Code snippet automatically formats the date labels on the x-axis to prevent overlap, which is crucial for time series plots. Code snippet adjusts plot parameters for a tight layout, preventing labels from overlapping. Error metrics bar chart visualization. Download the code on one PageCode Substack. Explanation of error metrics bar chart. Data preparation. Lists are created from metric names and their corresponding values for both models. Bar chart creation. Code snippet is used to create two sets of bars, one for each model, slightly offset to allow side-by-side comparison. Code snippet and code snippet. These lines ensure that the x-axis ticks are correctly placed and labeled with the metric names. Code snippet function. This helper function iterates through the bars and adds numerical labels, the exact error value, on top of each bar. This makes it easier to read the precise values without constantly referring to the y-axis. 7. Final footnote. Reforecast and model deployment considerations. After evaluating our SARIMA model's performance against a baseline using rolling forecasts and confirming its superiority or understanding its limitations, the next logical step is to use the champion model to make a true future forecast beyond the available historical data. This is what businesses typically need for planning. Download the code on OnePageCode Substack. Explanation of final future forecast. Retraining on full data. For the final forecast, it's best practice to retrain the chosen model on the entire available historical dataset, code snippet. This allows the model to learn from all patterns observed so far, providing the most informed predictions for the future. Code snippet for future. We use code snippet again, but this time, the code snippet index is set to code snippet, the index immediately after the last observed data point, and code snippet extends for the code snippet. Confidence intervals. Code snippet also provides confidence intervals, code snippet, which are crucial for understanding the uncertainty around the point forecasts. A wider interval indicates higher uncertainty. Future index. A code snippet is created to generate appropriate datetime indices for the future forecast, ensuring the forecast is properly aligned in time. Download the code on OnePageCode Substack. This visualization clearly shows the historical data extending into the future with the model's predictions and their ASO. Cited uncertainty, business recommendations, and continuous improvement. The quantitative evaluation, e.g., the SARIMA model achieved a MAPE of X%, significantly lower than the naive seasonal baseline's Y%, directly translates into actionable business recommendations. For instance, if the SARIMA model consistently outperforms the baseline, it can be recommended for production planning. More accurate forecasts lead to optimized inventory levels, reducing waste or stockouts. Resource allocation. Better predictions of demand can inform staffing, budgeting, and supply chain decisions. Strategic decision-making. Reliable long-term forecasts can support business expansion plans or new product launches. This evaluation process is not a one-time event, but part of a continuous model improvement cycle. As new data becomes available, the model should be periodically re-evaluated and potentially re-optimized to ensure its continued accuracy and relevance. This might involve monitoring performance, regularly tracking actual versus predicted values and recalculating metrics. Retraining, periodically retraining the model on the most recent, expanded dataset. Re-optimization, if performance degrades or data characteristics change, rerunning the parameter optimization process to find new optimal code snippet orders. Exploring alternative models. If significant shifts occur or the current model consistently underperforms, considering entirely different modeling approaches, e.g., profit, neural networks, ensemble methods. By following this rigorous approach to forecasting and evaluation, you can build confidence in your models and derive valuable insights for data-driven decision-making.